Okay, so last time we stopped here somewhere, I believe. Right, so we were talking about diodes. So we said the conduction condition for diodes and the blocking condition for diodes will depend on the circuit, right? So if the circuit is such that the circuit is forcing current to flow such that ID is positive, then the diode will turn on. If the circuit is forcing this VD voltage to be negative, the diode will turn off. Yeah? It has no control over its surroundings, right? So the diode is called an uncontrolled device. So this is in power electronic circuits. We will have three categories of devices: uh, uncontrolled devices, controlled, semi-controlled devices, and fully controlled devices. So there will be three families that we will talk about, and I will classify them later in a slide. So this is an example of an uncontrolled device, meaning the circuit affects its turn on and turn off characteristics here. So when a diode turns on, we know that there's a forward voltage that opposes the current, right? So if the current is flowing in this direction, there's a forward voltage opposing this current when the diode conducts. When the diode is blocking, it's an open circuit. Ideally speaking, it's an open circuit. When it's conducting, from a power electronics perspective, there is a forward drop. This forward drop we can see in the characteristics of the diode that you've studied before, right? So the characteristics of the diode is such that when current is flowing, so this is a value of current that's flowing, there is a value for VD, this forward drop. This VD is the forward drop across the diode. So there is a value for VD when current is flowing. So if current is flowing, there is some forward drop across the diode, meaning there is what? When current is flowing, there is a power loss as well, right? So there is a power loss that you will see with a diode that the diode will experience. Zoom in, right? So we would like to then overlay these this is the real characteristics of the device, real characteristic of a diode. Remember when we talked about the MOSFET, and we'll talk about it again, we drew the real characteristics and we said in power electronics we use it this way, and this is sort of an approximate characteristics when it's on or off, right? So we will go through the MOSFET again, but for the diode we do the same thing. So this is the real characteristic for diode. When current is flowing, there is a sort of a voltage drop across it. When VD is negative, there is no current flowing, but the diode is blocking. And then at some point, when you reach the breakdown voltage of the diode, then the diode will break down and you've destroyed it, right? So this is the characteristic of the diode. We will transition this into an ideal characteristic. Ideal characteristics meaning this ideal switch thing concept that we talked about before. This ideal switch concept says, if this forward voltage is very, very small, then just forget about it in the ideal characteristic and just draw the characteristic of the diode like this. When the circuit forces current to turn on, the diode will conduct current. Right? This was the y-axis, so it's on here, and there's zero voltage across it. Almost. It's a small voltage, right? So there is zero voltage across. And then when the diode is off, or when VD is negative, the diode is off. Okay, so this is the ideal characteristic of the diode, right? So when it's on, it's conducting current, all values of current in a positive ID direction only, no negative ID current, and this negative portion we will talk about briefly now, but there's no negative current when it's conducting, and there is no current at all when VD is negative, right? So that's the ideal characteristic. And it's close enough because the VD is small. That's fine. Or we can use that to design our circuits and simulate them. And then when we want to worry about loss, we have to make sure we go back to this real characteristic. That's the use of the real characteristic. The reverse recovery thing is something we started talking briefly about last time, and I'll illustrate a little bit more today. So through a circuit. I think it's easier to do it when I talk about a circuit. So last time or the time before, we were talking about this MOSFET sort of voltage divider, right? We said that we can build a voltage divider where this is maybe a LC filter, for example, right? We said this is a simple power converter, right? In power converters, though, there's something we need to note. So these LC filters are typically going to look like something like this. and an inductor here and a capacitor here, and we'll go through the design of these later. But for now, we have an inductor in series with current, the current flow path, right? So this is where the current flow is flowing, and there's an inductor in series. What do we know about inductors and current? Do inductors allow current to change abruptly? Right? These are the equations for voltage and current across voltage across an inductor and current through an inductor. Correct? This is current through an inductor. What current through an inductor is the integration of voltage across the inductor. So integration is basically what, like a summation, right? So if there is a voltage across the inductor, if that voltage is a DC voltage 5 volts, right? Here, 5 volt DC is now across the inductor. What does the current look like? It's a ramp, right? Assuming there's no resistance. I mean, your exponential is assuming there's some sort of resistance, right? But if there's, I don't have any resistance here, it's just a voltage across an inductor, pure inductor. Then if this is DC, then the integration of a fixed value is a ramp, right? So it's going to be a ramp plus some IL of 0, right? So I have some starting initial value of current, for example, and then I have a ramp, correct? So if this is the case, that means that inductors do not allow current to change abruptly. So even though, so now let's say I bring this voltage down to negative. What will the current do? It will slowly go down, right? It will not do this, right? Inductors do not allow sudden changes in current. Sudden changes, I mean, because of the fact that it's the integration of the voltage, then it's basically a summation of areas under the voltage curve. If this area is negative, it happens to be negative, fine. It's a summation of the area. So the area before was positive, now it's negative, so the positive value will decrease a little bit. Right? That's what happened. The positive value of current decreased a little bit. Right? So it was positive, it decreased a little bit because of the small negative area that I've added here. Right? So inductors do not allow sudden changes in current. Same thing, capacitors. They do not allow sudden changes in voltage. It's the opposite. One is voltage, one is current. So if that's the case, if sudden changes in current are not allowed, and that's why I actually put this inductor here, it means that basically this current is sort of continuous, right? This current is a continuous current because it's not allowed to change. It's not allowed to go down to 0 as soon as the switch opens. It's not allowed to do that because of the inductor being there. So I put a video on the site that illustrates what happens when you open a switch. Yeah. So if what if I do open the switch? What happens? When we talked last time, we said as soon as I open switch, current will be 0, right? We know. Do we agree now that that's not going to happen? Okay, so it's not going to happen. So in power systems, I'll show you what happens if you try to open a switch on inductive current. But this is a much higher voltage switch, right? So this is a switch that was actually open when current was flowing. So it's called an isolating switch. So it's and this is what will happen. Why is that? So what you just saw is an actual power system. So it's an actual isolating switch in a power system. It's like what we call a single pole, single throw switch. So this would be the switch. So this would be the switch pole and throw, for example. We'd call it a single pole, single throw. Like when you go and buy a relay or a contactor, it will tell you, it will ask you how many contacts you want in there. You probably, maybe if you were in the contracting or construction business, you probably saw many contactors put in different places when you want to, maybe create a startup circuit for an air conditioning system, or you will want to turn on loads and turn off loads in sequence in a certain fashion, and you will do that using contactors. So your PLC, your programmable logic controller, will probably send outputs to contactor contacts to turn on and turn off, etc., etc. So these are turning on and turning off power contacts. Yeah. So at low voltages and current, it's no problem. But in a power system, you saw what happened, right? But why is that happening? So there is inductive current. So we agree that current is flowing here, and it's continuous current because of the inductor, right? So what happens if I try to interrupt continuous current flowing through an inductor? It doesn't like it because of this equation, right? So if you try to change current that has a value, change it considerably, right? So you make a big DI in a small amount of time, so big DI and small dt, what happens to the voltage across the inductor? It becomes very, very high, right? And then we know that, okay, so this is a circuit, right? A circuit will behave according to Kirchhoff voltage law. So this is very high voltage across the inductor now, some voltage across your load, some voltage from your battery. So where is that extra high voltage that is created across this inductor going to be seen? Where will you see it? The voltage here will not change, right? The voltage here will not change, right? Because this is the IR is the voltage across this load. So this has some very, very high voltage. It was just generated because of the fact that you opened the switch. Where is it going to appear? It has to, everything, Kirchhoff voltage law, the sum of voltages has to be zero, right? So if the sum of voltages have to be this plus this plus this plus this is zero. This will not change. This will not change. This changed and increased considerably. So something has to be equal and opposite to this voltage in the circuit. No. In this loop.
This is kind of short out here in MOSFET.
No, but the voltage will appear across the. Remember, the MOSFET is opening. It's because the MOSFET opened. Now the voltage increased, right? It's the MOSFET that will. I mean, this is the voltage here. So this is V1 plus V MOSFET plus VL plus VR is equal to 0. This VR is not going to change. You have a certain amount of current that was flowing in there, and now it's actually decreasing because you tried to open the switch. This VDC is not going to change, right? So at the end of the day, if this doesn't change this, and say let's remove them out of the circuit. So basically, I have the voltage across the switch is equal to the voltage across the inductor. That's basically my Kirchhoff voltage law. This plus this equals 0. So this equals this, or this equals negative this. Doesn't really matter, right? As a magnitude, right? So the voltage across the switch is actually equal to the voltage across the inductor, basically. So now when you try to open the switch, voltage across the inductor went shooting through the roof because you changed from a high value of I to a small value of DI, to a small value of I. So your DI is big. And you did that very quickly. Suddenly you just opened. So dt is very, very small. So the di by dt is a very, very large number. So V is a very, very large number. So now the voltage across the switch is huge because of what you did, right? And that's what happened in the video. In the video, the voltage across the switch became very, very high, so it created an arc. Remember, air has a breakdown, everything has a breakdown voltage. Air's breakdown voltage is 30 kilovolts per centimeter. So this is a 500 kilovolt switch that we saw. You open the 500 kilovolt switch on an inductive load, so the V shot through the air, so it became a lot more than that, and it broke down the air. Air's dielectric material. It broke it down because the breakdown of air is 30 kilovolt per centimeter. It broke that down and created an arc. So then when you open these contacts, this arc, the arc expanded, increased in length, so it decreased in power because the bigger the arc, the more basically the current, it's basically current flowing through an impedance. So they try to make the arc very huge, or this distance between the electrodes larger and larger and larger until they dissipate the energy that's in the inductor, basically. So they dissipate it, the arc quenches now. Right? So that's what you saw. So in power electronics, we don't have these big arcs. Otherwise, we will see this thing burning up, right? So we don't have these big arcs. And the power electronics people had to find a solution to that. So what they did was a clever solution. So how about if I add a diode here? What will that do to this scenario that we just described? Remember what happened was, because we opened this switch, this inductor voltage went shooting through the roof because it's continuous, right? So now, and because it's continuous and it went shooting through the roof, I was gonna keep burning this, this switch would see crazy voltages across very high voltages, and these arcs that we just saw will always be appearing. So this thing will be glowing, right? So this is not what we want to do in power electronics. So we had to find a solution. So typically, if we insert a diode here, what would happen? So we said that the current here is continuous, and that's why this VL di by dt was going to go high, shooting through the roof. So if the current here is continuous and I put a diode, what's going to happen? Now I open my switch. What's going to happen to the inductor current? Is it going to be interrupted? It's not going to be interrupted because inductor current will continue flowing through the resistor, through the filter, through the diode. It has a path through the diode. There's no path through the power supply anymore because this switch is open, right? But there's a path through the diode, right? So now I don't have this problem of switches arcing like an isolator in a power system, right? So typically, and that's where, you know, it's the uncontrolled device being used in this circuit is a very clever idea. It's basically eliminates this problem that we see in arcing in power systems. And it's not just in power systems. In your houses, you would see the same in the switches, in your light switches at home, right? Again, your circuit at home is a piece of wire with current flowing through it, right? If you go back to your 322 material, you will know that you can calculate the inductance of this circuit. It's a wire with current flowing through it. There's a magnetic field set up around it. You can calculate the inductance of that circuit here. So that circuit is just big, a value of inductance. So when you turn on and turn off the switches in your light, in your room, you will see arcing behind. And that is because of the inductive effect that we just talked about, right? And we can live with that in a low voltage circuit, no problem. It's not like it's not allowed. You can live with that in your house. It doesn't bother you. But in a power electronic circuit that's inside this thing, I cannot, because there are other power electronic devices around it. If it keeps arcing and breaking down the air around it, it may ruin the rest of the circuits. It will burn the board. It will, it's not something that you can handle safely. Versus in a switch that's behind and inside the wall, fine. If it arcs a little bit and the contacts erode at some point, you change that. It doesn't really bother you, right? So in power electronics, we created this alternative path for the current to flow through this diode. So what happens when the diode starts conducting, in this case, because the switch opened, right? How about when the switch turns on again? Fine. Exactly. So when the switch turns on again, what is the voltage that I put here? What voltage does this node see? When the switch is on.
5 volts.
Exactly. So the V1 or 5 volts or this positive voltage. So I put this voltage, the highest positive voltage across here, and I've put this negative voltage across this negative voltage at this point in the diode. So what will this do? We said that the diode will block if my cathode sees a positive potential and my anode sees a negative potential. So basically VD is negative, right? So what do I have here? I created this VD is negative thing, right? This point here sees a positive voltage and this point here sees a negative voltage, right? So I've put a reverse voltage across the diode and blocks. Okay? And then when the MOSFET is off, this positive 5 volts is no longer here, and current is actually flowing in the inductor, and it has to continue to flow in the inductor because inductors, this is their characteristic. They do not allow currents to change abruptly, so they will force current to flow through the circuit. Where will it flow? No path through here, the MOSFET is open, it's going to have to flow through the diode. Right? So during this transition from the diode being on to the diode blocking. Remember the MOSFET, as soon as it turns on, the diode will block. Correct? So during this transition, we said that this diode characteristic is a bit special, right? It was conducting current, and then until this MOSFET turns on, it will stop conducting. Fine. During the transition, there's something else that happens. So it was conducting current, but for it to start blocking, so for it to block, as soon as you apply voltage, it wants to start blocking. For it to block, it has to go through a transitional phase where all the stuff that you studied in 370, where you have a depletion layer, and as soon as you have the proper characteristics for the device to turn on, electrons and holes will flow and all that kind of stuff that I do not know and I don't care to go through in the class. That depletion layer will have to build up again for the diode to block, right? And that is done through, instead of, okay, this was the positive current direction to the diode, right? This was how current was flowing through the diode when it was on, right? Now the diode wants to turn off. For it to turn off, what did we see here? This was on, positive current, and then there was a period where current was negative, okay? And this happens like this. So current was on in the diode, and the diode was on, so current was flowing in this direction, and now the diode wants to block. For the diode to block, according to characteristics, the current, the waveform that you saw, there is a negative current that has to flow, right? So how is that going to happen? So what happens is, as soon as the switch starts to turn on, the switch wants to turn on, the diode wants to block. So what's going to happen is the diode will not block as soon as the switch starts to turn on. There will be a period where the switch is on and the diode is on at the same time, right? And this period is what happens if both of these devices are on. If both of these devices are on, current's going to flow out of the battery through the switch, and now it has two places to go, either here or here. This is like a short circuit, right? The switch diode is on. It's the ideal switch is on. This is, high impedance path. Where does current like to flow through? High impedance? Low impedance path, right? So current will flow through the, ideal switch, which is the diode in this case, because it's still on. It's not able to block. So it will flow here. So it will do this negative current thing that we wanted to do, that the characteristics require for the depletion layer to be built up again and the diode to start blocking, right? So there is a period of time that I'm actually putting a short circuit across my supply, which is not good, right? So because that's not good, and because we don't like it, and batteries don't like to be mistreated, then remember the reason why we put this filter here was to make this current nice and smooth, right? And output voltage and current nice and smooth. So same thing, we will end up looking at filters that we will put here as well, so we don't mistreat the battery or mistreat our power supply, our source, right? So because of something like this, not just this characteristic, there will be other things that we talk about later, but this is one of the reasons we will do something like that, right? If we do this filtering, then we will treat the battery better. We will allow this to happen because we know that there are certain times where there's significant changes in current and voltage required by the load, and we will treat that, use a filter to make sure that we handle that properly. We will talk about that later. But now, after this short period of reverse recovery, so it's called reverse recovery time, after this short period of reverse recovery time, now the diode blocks. If the diode blocks, finished, the MOSFET is on, and we go back to the same thing. MOSFET is on, diode is off, current is flowing, MOSFET tries to turn off, the diode will pick up and conduct, because inductor current is continuous. Okay? So, and this reverse recovery time is a characteristic of the specific diode that you choose, right? So if this reverse recovery time is long, is that a good thing or a bad thing? I mean, is this reverse recovery useful to my energy conversion process? No. Is it useful to the input to output power transfer? Let's talk about it now. It's not useful to the input output power transfer because what it's doing is it's shorting my supply. It's not behaving. It's not turning. When the device is on, it's useful for me, and when the device is off, it's useful for me. During this transition period, fine. The circuit is transitioning. I cannot do anything about it. It's the physics that's playing. I'm not really counting on that for the energy conversion process to be performed. The energy conversion process is performed when the MOSFET is on, diode is off. When the MOSFET is off, diode is on, and that's how I'm doing my square wave pulses. But during this transition time, it's not useful for me, but I have to live with it. Okay, so it's because I have to live with it, and it's actually current flowing through my circuit, and we will see, and we saw that this current is actually flowing through where? It's actually flowing through my MOSFET and through my diode, right? And both of these devices also have voltage drops across them during that period of time when they're conducting, right? That means there is power loss. right? So it's really a pain that I have to live with something like this, and not, and it's not something that I really well like, and it's not very useful for my power conversion process. So it's a characteristic of a specific diode that you've selected. So so it's going to cause some extra power loss, and it will require some special filtering requirements. So it's not something very nice, but you have to live with it depending on the diode that you choose. Expensive silicon carbide diodes do not have, or I don't want to say do not have minimal reverse recovery time or charge. So it's a reverse recovery charge that has to be removed so that you create a depletion layer again. So it requires time for you to remove that, right? So expensive silicon carbide diodes don't have that at all. For example, for all practical purposes, you can assume they don't have that. Cheap silicon diodes have a lot of reverse recovery time, right? So if you want to build a space grade power converter, you will probably go and choose diodes that are expensive. They don't have reverse recovery time because you don't want the loss. Also, if there is a reverse recovery time, okay, and you want to build a high frequency switching power converter, that's also going to limit your switching frequency, right? This is time, right? If you want to increase the frequency of your pulses, and we will see why we want to increase that. If you want to increase the switching frequency of your pulses, then you don't want something to take up time that's not going to be useful. So this is taking up time that's not useful. So it will limit your switching frequency for sure. By how much? By you need to do the calculation. You have to remove that from your ability to switch fast. If you're considering that you will switch off and then back on here, can you do that? I cannot. I cannot switch off here and then back on here. I cannot, because there's reverse recovery time. The diode is still not blocking, right? So it will limit switching frequency. It will increase losses in both the diode and the MOSFET because it's flowing through both, to require some additional filtering requirements. So all of these things, right? That's on the cheap side, right? Then you go on the expensive side, you use silicon carbide, or if you are if you're building a low voltage application, you can also use what is called a Schottky diode. I think I wrote that here. Yeah. Schottky diodes also have negligible reverse recovery diodes. So Schottky diodes and silicon carbide diodes don't have reverse recovery time for all practical purposes. Okay, that's diode. Any questions? So this was an uncontrolled device. The thyristor or SCR is a example of a semi-controlled device. And there are many different families of it I'll talk about. And it's exactly like a diode, except that you can turn it on in a controlled fashion, right? So the exact same conditions as the diode. So as soon as it has, that's why it has an extra terminal. It has an extra gate terminal. For you to turn on, for you to be able to control the turn on of the device. So it's like a diode that you can control its turn on time. So if the circuit would like to flow positive current through a diode, it will do that, right? The diode will turn on, right? But if it's an SCR, then the circuit is still trying to force some positive current flow. It will not turn on unless you provide the gate signal. If you provide the gate signal, as soon as you provide the gate signal, this device behaves like a diode until current becomes zero, or current tries to go in the opposite direction, right? So until current tries to go in the opposite direction, and right after you've turned on, this device behaves exactly like a diode. So if it behaves exactly like a diode, the characteristics will look very similar. When the device is on, I can conduct any amount of current, right? And there is zero voltage across it. When the VAK is negative, then the device is blocking, right? If VAK is positive, this is a condition for the device to turn on, right? But if you have not applied the gate signal, the device will still be off. Okay, so that's what this means. It's VAK, even if it's positive, right? In a diode case, if VAK is positive, that means that the current will flow, right? But in an SCR, even if VAK is positive and you've not provided the gate current, it will still be off. As soon as you provide the gate signal, it will turn on, right? And behave like a diode. It will behave like a diode until you try to push current through it in the opposite direction, like a diode. If you do that through a diode, what's going to happen to the diode? It will block. Current cannot flow in a negative direction through a diode. So as soon as you try to do that, or the current becomes zero, basically, if the current goes to zero and tries to flip direction, it blocks. Okay, so that's an SCR. And so people call them SCRs or thyristors, does not really matter. Then people came up with, okay, this is really interesting and really nice, but it's a semi-controlled device because I can only control the turn on. Then people created other thyristors, right, that have additional benefits as well. So they said, okay, thyristors are nice and SCRs are nice, and actually it's the workhorse of high power. Okay, so high power converters, it's the workhorse of high power converters, and we will see some charts now for different ratings of devices, but it is the main workhorse of very high power applications. Yeah. So we can turn it on, but we cannot turn it off. Turning it off is by the circuit, right? Circuit conditions dictate when it turns off. As soon as current tries to flow in that direction, it turns off. So what people developed after that was they saw this shortcoming and they said, okay, let me try to develop a thyristor or an SCR with a turn-off capability, but I do not want, for example, in here the gate. Remember your 325 course, if you take in 325, that each device has sort of a beta, or the HFE. Sorry, what is it called? The HFE of the device. It's the gain. Sorry, each device has a gain between the gate and collector, right? So BJTs would have a certain gains. Different MOSFETs would have different gains, etc., etc. So the gain in an SCR is so the gain. Sorry, so this one SCR, I can turn it off. I can turn on here only. So people develop what is called a GTO. A GTO is a device that you can turn off. It's an SCR that you can also turn off, but the gain of this gate drive, remember this is a gate drive, right? I can turn it on and turn it off. That turning on is very simple. It just requires a simple pulse, right? But turning off the device, they found that the gain was very low. So for you to turn off the device, you required a lot of current to be pushed to the device to turn it off. Okay, so this is simple. SCR is simple, right? You just apply a pulse, and you don't need to maintain the pulse actually. It's just a simple pulse, and the device is on. So if I have a circuit like this, and this is my input voltage waveform, what will my output voltage waveform look like? And what if, so this is case 1, case 2, I put this pulse right here. What would my output voltage waveform for case 1 look like and for case 2 look like? This is an AC waveform, right? This is an input waveform. After, when you give this gate pulse, right, it's going to look like a diode, right? So what will, if I put a diode here after this gate, so before the gate pulse, what does it look like? Open circuit, right? It's an open circuit. After the gate pulse, it looks like a diode. Think of it like that. It looks like a diode until the diode will also stop conducting, right? The same condition for the diode to stop conducting, thyristor will stop conducting. Exact same condition, right? Except that the diode, as soon as the circuit allows it to conduct again, it will conduct again. Thyristors will not, right? So what happens in this case then? If you put a diode after, so at the beginning, it's open circuit. So if it's open circuit, what does the output voltage here look like? If there's an open circuit here? If it's an open circuit, this is open. What does the output voltage look like? 0. So it's 0 until here in the first case. And then what happens after that? Exactly, right? If what happens after that? Okay, think of this after that as a diode. If there's a diode, this is negative voltage, this is positive voltage. You're putting positive voltage here and negative voltage here across the diode. The diode will not conduct, right? So it will remain zero. How about the second case? Until, okay, let's agree that, okay, until here it's what? Open circuit. And then? And then, remember, power electronics, it's either open circuit or short circuit, right? There's no, because ideal switches, right? So initially it was open circuit, and then after that, is it going to turn on? If it's going to turn on, it looks like a short circuit, or it looks like a diode. Sorry, it's better. I mean, it looks like a short circuit for a while because it's a diode. If you put a diode here, it would have done what? Turned on, because this is positive voltage. I'm putting some positive voltage on this side and negative voltage on this side, right? So there's more positive voltage here than here. So I've created the condition, and I have an impedance, and this looks like a short circuit. So I have all the conditions for the current to flow. So current will flow, ID will flow positively through the diode, right? So this behaves like a short circuit because it's an ideal switch. So the output voltage will jump here, follow the input voltage, right? So I'm basically this looks like a short circuit. So I have the input voltage put across my output load, right? Until what happens at this point? What is the current? So this is voltage, and then I have a resistive load. So voltage and current look exactly the same, right? So what's going to happen at this point? Beyond this point, if you have a diode here, what's going to happen to the circuit? This was a diode, and now my voltage input here is flipping polarity. It's flipping polarity. What is, if I have a diode here? Forget about, if I just have a short circuit here, what would have happened? No, if it was a short circuit, current was going to start flowing in the opposite direction, right? So we said that if current tries to flow in the opposite direction, in a thyristor, what's going to happen to it? Or a diode? It will block, right? Diodes will only conduct forward current. If you try to push reverse current through them, they will block. So it's exactly the same thing. So at this point here, it blocks, right? So as soon as it blocks, it's an open circuit. It does not see anything because you did not supply any gate pulses at all after that. It just blocked. That's it. It will not turn on again until you provide another gate pulse, right? So that's the thyristor. Okay. That's nice and dandy, right? And this created a certain output voltage, right? People said, okay, no, this is nice, but I also want, let's say I want to create, voltage only between this angle here and this angle here. What do I need to do? I need to be able to turn on the device as well as turn it off. So I only want voltage to look like this, for example. I want a smaller voltage, smaller RMS voltage. So I need to be able to turn off the device as well, not just turn it on, right? So people said, okay, let's design something like that. So they came up with the GTO, the gate turn off thyristor, right? So the GTO was nice. It provided that capability, but it required a large gain. So for you to turn it off, turning it on was very easy. Turning it off was very painful because it required a lot of current, a lot of gate current to, like, the BJT. BJT is a current control device. There was a current gain, and you had to provide a certain amount of gate current continuously to the device for collector current to flow, right? MOSFETs were different. What was a MOSFET? Was it a current control device? Did you have to provide continuous gate current to the MOSFET? No. Voltage, yeah. MOSFETs are voltage control devices. They're like a capacitor input voltage control device. As soon as you charge the capacitor at the input, the device can turn on, right? And capacitors, for you to charge them, if you bring me a capacitor like this, I will put the voltage source across it. Its voltage will go up, and I can remove the voltage source. The capacitor voltage will remain there, right? So I can provide a gate voltage. I don't need to provide continuous current. I can keep the voltage across the capacitor, but is it going to consume current? The capacitor, the MOSFET's gate looks like maybe a small R and a big C here. If I charge this, and I've charged my gate capacitance, it will remain charged. There will not be a continuous current being sucked from my power supply, my gate source, my gate power supply, right? So that's why it's called a voltage control device, not a current. As soon as the voltage across the gate capacitance is a certain value, that threshold is enough for you to turn on the device. You don't need to maintain current in the gate. That's why people like MOSFETs. They really like MOSFETs because of that. So the gate turn-off thyristor, you can think of it more like it's a current control device, and you required a lot of current to turn off the device, right? So that was okay because it did a very nice thing for people. They gave them the ability to actually control the turn on and turn off of power, especially at very high voltages and high currents. So people loved it. It was great. But people said, okay, I can do better. So they came up with, I don't have a picture of it here. They came up with what's called an MCT. So it's a MOS controlled thyristor. So an MCT is a second generation GTO. So instead of, it behaves exactly like a GTO. So it's a diode, and then they've added the turn on and turn off capability like a GTO, but the turn on and turn off capability is voltage controlled, not current controlled. That way they combine the best of everything, right? So voltage control gate means that they don't need to maintain a huge amount of current. And remember, these devices are used at very, very high power, so pushing thousands of amps through them. So if the gain is not very high, then I need to push hundreds of amps through the gate to turn off the device. Now people said, oh, wow, we can come up with a MOS-controlled or MOS-type gate for the thyristor or for the GTO, right? So it's called an MCT, MOS-controlled thyristor. And now it's a voltage control device. So MCTs are voltage-controlled, sort of controlled thyristors or GTOs, versions of a GTO, right? So you see the differences and the progress. Of course, these are more expensive. The MCTs are more expensive. The thyristors are dirt cheap, right? Depends on your circuit, right? It depends on the circuit. Okay, so we discussed the thyristors were the semi-controlled device. Now, the last type of device we talk about is the fully controlled device, right? So transistors are the fully controlled devices. Again, we talked about this before. So we do not operate them in the linear region. So in the linear region, they behave like what you did in 325. So we do not use that at all because they have considerable loss, right? We said that's a considerable loss. Why? It's because if you go into anywhere in the linear region here, anytime you have any value of current, there's a considerable voltage across the device. And you don't want to do that. You want to operate here, right? Across, this is the line where you will really operate. And then, the ideal characteristic is sort of pushing this line to the left side. So you have this is sort of the switching characteristic of a MOSFET or transistor, right? So in these devices, when the device is on, there's almost zero voltage across it, and we said the zero voltage comes from the fact that this slope is the relationship between I and V across the device. It's a linear relationship, and we know that the V and I are related by the equation V equals IR. So this slope here, since it's a fixed slope, is actually happens to be the RDS(on) of the device. And we saw that with a device that, for example, we're going to use in our experiments, it's an 8 milliohm, right? It was a very, very small amount, very small resistor. So that's why we can sort of assume that this is, ideally, it's sort of a straight line. When the device is on, there's 0 volts across it almost, and it's conducting current. When the device is off, it's blocking current, blocking voltage, right? It blocks positive voltage, right? If VDS is positive, it blocks that voltage. How about if VDS is negative? If VDS is negative, MOSFETs actually happen to have a body diode, what it's called, it's a parasitic diode. Because of the structure of the MOSFET, inherently there's a parasitic diode that's in the design. You cannot remove it. It's because you're building a MOSFET, you're also building a diode with it. Again, we were not studying device physics or device modeling, but that's what happens. When you're building a MOSFET, it just comes free. And the problem is these MOSFETs these diodes are typically very poor because they have very horrible reverse recovery characteristics. right? So it's just from the structure of the MOSFET, you end up with a parasitic diode, and this parasitic diode, you end up not being able to optimize its reverse recovery time, right? Because you're building a MOSFET, you're not building the diode. So people now in the device area that are working on MOSFETs, they try to build better MOSFETs with better body diodes. They call it a body diode or parasitic diode. Okay, so that's why if you put a reverse voltage across here, if you flip the polarity of VDS, this actually will conduct current through the diode. Right? A MOSFET will actually conduct current through the diode. So you can actually use a MOSFET as a diode if you want, but a very poor diode. You can buy a MOSFET and you do that if you want. What else? So again, there are two types of devices that we talk about here. So MOSFETs and BJTs. BJTs don't have this reverse recovery, the body diode issue that we talked about. So a BJT does not have that, which is a good thing. Yeah, one of the nice things about the BJT. But from power electronics perspective, we will look at both of them as an ideal switch. They will both look as an ideal switch, and the characteristics again similar to a MOSFET's ID and VDS curves. For the BJT, we have the IC and VCE curves, and we do the same thing. We operate in saturation and cutoff. We don't operate in linear region. So the switching characteristics look exactly the same for a MOSFET and a BJT. They look exactly the same. When the device is on, it's conducting current with no voltage across it. Off, and it blocks positive voltage. The BJT is the same thing. It blocks positive voltage. So if it's open and VCE is positive, it blocks it. It's able to block that voltage. If VCE is negative, it will not function properly. In 325, you were going through and making sure that you were creating a collector voltage that's higher than the emitter voltage for current to flow. Remember, you were doing the bias circuits in 325? You were building all these resistor circuits and looking at voltages across the devices here, voltage across the device, from collector to gate, from collector to emitter, emitter to collector. You were looking at all these voltages using these bias circuits, and you were doing that to create these amplifier circuits, etc., etc. And none of these circuits, you had to make sure that the collector voltage was higher than the emitter voltage for the device to operate properly. And it's the same thing with the MOSFET. You had to make sure that the drain voltage is higher than the gate voltage, than the source voltage for the device to operate properly. Okay. So any questions on the use of the devices as this MOSFET or the BJT as a switch? Again, it's nothing but a switch. Nothing but a switch. Okay, and in reality, there is a voltage drop across the MOSFET because of RDS on. How about in the BJT device? What is the voltage drop across it equal to? Yeah, it's VCE, and that was, you were always considering that was what? 0.7 volts, right? In your 325 courses, you're already considering that as 0.7 volts. So and that's typically the same voltage drop also that you considered for the drop across the diode, the forward drop of the diode, right? You were using that as well. So in low power circuits, typically, yes, a 0.7 volt is okay, acceptable to use. But for example, in power electronics, it would be different. So for example, let's look at this diode. And let's look at the forward drop across this diode. Here. So it's the forward voltage across the diode. There you go. Forward voltage across the diode at 3 amps is 1.2 volts for this diode, right? So in power electronics, this 0.7 volt is not something you take for granted. 0.7 volt all the time. Right, in 325 circuits, yes, you can do that because typically, these devices are very low power, very low voltage. They're all very similar. In power electronics, we're talking about voltages ranging from what? We're creating power supplies for, sensors that need to amplify nanovolts. So typically, these power supplies will be a lot lower voltage than a power supply used to transfer power between Qatar and Saudi Arabia. This is at hundreds of kilovolts, right? So the range of devices is huge in power electronics, right? So you cannot just take it for granted. Okay, 0.7 volts, right? The forward drop across the diode. You will go to the data sheet and take it out, bring it out to the data sheet, extract it from the data sheet. And that's then how you can calculate the losses. It's a forward drop multiplied by the current flowing through the diode. And with the MOSFET, it's the current I squared times RDS on. And for the BJT, the loss is what? It's the collector current multiplied by the VCE voltage, collector to emitter voltage. And the collector to emitter voltage is a junction voltage, like the diode junction voltage, right? And you will extract it from the device's data sheet, or we will give it to you in the problem. Okay? But they have losses. In reality, they have losses. It's not pure 0 volts across the device when the device is on. Okay. So now what else? So these are we talked about what? We talked about the uncontrolled devices, which are the diodes, semi-controlled devices, which is thyristor. SCR is easier, right? SCR is easier, and then fully controlled devices, the transistors, which are the MOSFETs or the BJT device. And then BJT devices, there's some interesting variation of that. So BJT devices, they are what? We said they are current controlled devices, right? So I have to keep supplying base current for the device to turn on, because these devices have gains, certain gains that, dictate the value of collector current passing through will require a certain amount of base current. The power electronics people did the same thing they did with the thyristor to the BJT device. They created what's called an IGBT. Okay, so it's called an IGBT. So it's basically they took a BJT device and they did this to it. This looks like what? Like the MOSFET's input gate, right? So, and that's what this IGBT is. So they took a current-controlled BJT device and converted it to a voltage-controlled device. The beauty is this. MOSFETs have these parasitic diodes. They are very difficult to construct for very high voltages and very high currents, especially because of this poor diode, right? So BJTs are beautiful. BJTs are an excellent kind of device. You can push it to very, very high voltages. You can push it to very, very high currents. It's great. The drawback in power electronics circuits is the fact that it's a current-controlled device. I need to keep pushing current. And if I want to do an efficient power conversion system, I don't want to keep pushing current in circuits without a use, right? So if it's just going to allow me to turn on the device, come on, let me find another device, right? So they took the BJT and they created what is called an IGBT. It's called insulated gate bipolar transistor. Insulated gate bipolar transistor. So it's exactly like the BJT. So it will have the same characteristic, VCE drop across it. Instead of being called a base, right? This will also be a gate, right? And then this gate here will act like a MOSFET's gate exactly. So this gate to emitter voltage is exactly like the gate to source voltage in a MOSFET, right? So that's beauty, right? Because you've combined the benefits of the MOSFET and the benefits of the BJT in a single device, and that is the actual workhorse of the bulk of power electronics. If you open almost any power electronics device, you will find the IGBT, almost. At very low voltages, no. At very low voltages, the MOSFETs are cheaper. Okay, so at very low voltages, MOSFETs are cheaper. They're faster. They can turn on and turn off faster, which means that they have some advantage in very low power applications, small, tiny applications. In very, very high voltages and very high currents, SCRs and thyristors are really the big workhorse. But then everywhere in between, the IGBT is the master, right? So open a motor drive for a fan, open a motor drive for an air conditioner, open a motor drive for whatever application, open a UPS, open I don't know, any power electronic device otherwise, you will find the IGBT. Okay, so that is the workhorse of the power electronics industry. And that's what you have here. I just drew it a bit differently. I don't like the way that the book draws it, honestly. Okay, so I have a slide in the next, and I'll skip the slides for now. But this slide here shows you how I draw, how I would like to draw our devices. It's easy. So I draw the diodes this way, SCRs this way, and then I will just draw the fully controlled devices all this way. Okay, I will just draw them all the same way. MOSFET I will draw it this way as well. MOSFETs actually, when you draw the N-channel type MOSFET, they draw it this way in the book. Okay, I think it's a bit confusing because the arrow is the opposite direction of where the current is flowing. So I just draw them. I mean, for simplicity, I will just draw it this way. So I'll draw the MOSFET this way. I'll draw the IGBT this way. Okay. And let me go back to here. So this slide, what do I show? Okay, so remember when I said about this, this simple power converter that we talked about, and we added a diode 2 here. We said we have some filtering stage that we add here, and this is my load that I have here. And we said that, is it something that I would like to see both devices on, or is it happening just because of the reverse recovery? During only the reverse recovery, both devices are on, but that's something in the transitional stage. So forget about that. From a power conversion perspective, either the diode is on, or either the MOSFET is on, and if the MOSFET is on, it is taking this 5 volts and putting it here across my load, right? And if the MOSFET is off, the inductor current is flowing through this diode. So what's my output voltage going to be? Remember, these are all parallel. Forget about let's say this is not an inductor. Let's say just the short circuit here. And what is the output voltage that the diode conducts? 0, right? Because this is a short circuit. And that's what we wanted to create, right? We wanted to create an output voltage that looks like this. 5 volts, 0, 5 volts, 0. That's what we wanted to do. Fine, it's filtered because of the capacitor, but this voltage here will be 0 when the diode is conducting, because the diode becomes a short circuit when it's conducting. So if there's a short circuit here, the voltage is 0. When the diode is an open circuit, and this happens when the MOSFET is on. So this is a short circuit, and this is an open circuit. So what's the voltage across the diode in this case? 5 volts, right? So it's output voltage, or the voltage here is 5, 0, 5, 0, 5, 0. So I would like to call this T1. I would like to call this node T2, and I would like to call this node, P. I'll call this a pole. Pole, P-O-L-E, right? And typically, if you in some texts, you will find that people call this thing here, maybe redrawn as this for. Here's the same, right? I just redrew it in a different fashion, right? This is my power supply, this is my inductor and capacitor, and load, right? Same. And this block here, people typically call a switching power pole. Switching power pole. Why do you think people sort of combine this block together? What did we talk about, this arcing thing that we talked about? This arcing phenomenon that we talked about is developed because if we use what is called a single throw, single pole device. So single pole, single throw devices, meaning, this is my pole, this is my throw, and this is my pole, right? If I have a single pole, single throw device, we said that if I have inductive current flowing, I will create this very high voltage and arcing will happen, right? So in power electronics, we don't have single pole, single throw devices. We don't do that. We have single pole, double throw devices. Okay, so single pole, double throw, meaning I have single pole here and 2 throws. Throw 1, throw 2. Right? So that's, in power electronics, we always have that. Why? Because we cannot live with this arcing business. Right? So we have to have an alternative path for the current to flow. So you will not find a power electronic circuit that does not provide an alternative path for current to flow. Always, there has to be. So you will always have a structure that allows current to flow in a different path, so that you don't create these extra high voltages and burn your power electronics device. So this block here acts as a what? Acts as the interface between my input power supply. This is my input power supply, right? And this is my load. I would like to convert power from this 5 volt, let's say, to 3 volts. Right? That's what I would like to do. And I stick in there a circuit that allows me to do that. Right? This circuit, if it is lossless, if it is a lossless circuit, right, then the power at the input is equal to the power at the output. Correct? Assuming the filter is also lossless, then the power at the input is equal to the power at the output. Right? So let's see what happens here. I need to, here I forgot to, sorry, I need to draw a line here as well. Should have done it. But now this is my typical, if you think of what you see here, this is, and are these two devices ever on at the same time? They're not on at the same time, right? So I typically have my switching power pole. This is T1, this is T2, and this is my pole. My MOSFET is either on or my diode, right? And I can switch, I can swap these MOSFETs. I mean, swapping them will do something different, right? In a different circuit, but I will show you these different circuits here. But I can swap them around, I can do whatever I want. But for example, in this configuration, I have one pole and 2 throws, okay? And these 2 throws, either the top device is on or the bottom device is on. I cannot have them both on. If I have them both on, it's a short circuit condition. It only happens during this transitional stage where there's reverse recovery. Forget about that. That's not important for a power electronic circuit operation. For loss, yes, it's important. So can I redraw this as this, where this is T1, this is T2, and this is my pole? Can I say that these are equivalent? I can, right? So either the top device is on. If the top device is on, current is flowing this way. Either, in this case, it's flowing in this fashion, right? How about if my bottom device is on? It's flowing in this fashion. Also, nothing prevents it from flowing in this fashion, right? So nothing prevents it. Whether it does it or not, it doesn't really matter. But for now, assuming there's something besides our basic circuit that we had here. Remember, our basic circuit that we had here, yes, nothing will happen. This will not exist. But if I had a more complicated circuit that does something else, we can consider that this may happen, yeah. Yes, ma'am.
Could you please just clarify what throw in the pole is?
Just a node in the circuit. Just a node, nothing physical here. Just, I mean, it's these two nodes. I will just call them throws. Right? It's and the pole I will just call this node here. I will call a pole. Okay? So I'm connecting this pole to either this throw or this throw. When I'm connecting this pole to this throw, it's like turning this device on. When I'm connecting this pole to this throw, it's like the diode is on, right? So in power electronics, I can represent almost any power electronic circuit using this block. Any power electronic circuit. Okay? You did not study any complicated power electronic, but I can make any circuit look like this somehow, right? So, and in this configuration, remember the current is always here. What? There's always current flowing to my load. Because do I want my load current to be interrupted? No. And I have a nice big inductor here to make sure that that does not happen, right? And we will discuss how to design it later. But current is always flowing into my poles from my throws, right? So current is flowing from my throw into the pole, from this throw into the pole. This throw, let's say, is at a certain voltage, V1. This throw is at a certain voltage, V2, right? So what is the power coming out of this throw? This is I1, this is I2. What's the average power that is coming out of this throw? Going from this throw to the load. Average power is what? Average voltage times average current, right? So it's average voltage times average current. So this is power that's going from this through this node into the pole, right? How about if this switch here goes and connects to this point here? What's the average power flowing from this throw into the pole? V2 times I2, right? And are they happening at the same time? I mean, is this power being transferred to the load at the same time this power is being transferred to the load? It's not, right? So, but the sum of them is equal to the power that's going to the load, right? The sum of the power going from this throw to the load plus the power going from this throw to the load is what constitutes a load power, right? So I can rewrite that as what? Average voltage and average current coming from throw 1 plus the average voltage and current coming from throw 2 is equal to the pole average voltage and average current, correct? So what does this tell us? This tells us that I've created a power conversion device. So I've created a conversion device that takes any two nodes from, let's say I have a power supply. In this case, I have a power supply, a battery here. In this case, I can connect a switching power converter or switching power topology and then connect a load. And this box here will do this average power conversion. So V1, I1 plus V2, this is terminal 1, and this would be terminal 2. V2, I2 is equal to VP average, IP average. So what does this look like? Can I increase power from my input to the output? Can I increase the power? Can I put P1 equals 100 and have P2 equals 200? No, I cannot. This is a constant power transfer device. It's like a gear, right? I can make V1 and V2 different values, and I can make VP different values, but then I have to make sure that I adjust I1, I2, and IP accordingly, right? So this looks like a transformer, right? Transformer, fine. I can create a V1 here and a V2 here that are different. Like this can be 10 volt, this can be 100. But if this is 10 volts, 10 amps, then this is what? This is 100 volts, 1 amp, right? So 100 watts is equal to 100 watts, assuming the transformer is lossless, and it's the same thing with a power converter, right? The power flowing from this node, the power flowing from this node into this box is equal to the power consumed by the load, right? So it's a constant power transfer device, yeah. So we will get into the waveforms later. I just wanted to make sure that's clear. And then we'll talk about one configuration and we'll come back later. So we talked about in our circuit here, I presented this circuit and we went through how it works, correct? And this circuit, my throw voltage was positive. So this was T1. This is T2. My throw voltage T1 to T2 was positive. And current was coming out of this node into the load, right? We found that the best circuit to do to put in this case is this configuration of MOSFET and diode, right? We will go back and find the justification, but I will show you a trick. So if for this sort of configuration where my VT is in this polarity and my current is going out into the pole, I use this circuit topology. How about if I want to flip current? If I had an application, for example, what's an example application of that? An example application is something that, let's say I have a battery here. Instead of just a load, I have a battery here. So I have a battery here and I put my load here. Can I use the same configuration of circuit? No. Why not?
Because one of your MOSFET up there can't backfeed.
Exactly. So current has to flow this direction in the MOSFET. Current has to flow in this direction in the diode, right? So if the current's coming from my battery here into this node, it's not going to find a place to flow, right? So this device selection was wrong for this application. For the previous application, it was fine. For the previous application, perfectly fine. Current was coming out this way, and voltage polarity was like this. Voltage polarity was like this. I am making everybody happy because the drain voltage of the MOSFET is higher than the source voltage. So we said that for MOSFET to be able to turn on and turn off, drain voltage has to be higher than source voltage. And same thing with the BJT. Collector voltage has to be higher than the emitter voltage for you to be able to turn it on and turn it off. So I've satisfied that condition in this case. And then current is flowing in this direction, so current can flow. I can turn on and turn off the MOSFET, and current can flow. And if the MOSFET is off, current can find a place to flow through the diode. So that's why this previous circuit works with using these selection of devices. But this circuit would not work, right? So one trick to do it without going through this logic is this table here, okay? So if your throw voltage polarity is such that it's positive, so I have positive throw voltage polarity, so meaning this throw is higher voltage than this throw, and current is going out into the load, into the pole, right? Then you can use this circuit. In the example that we just went through, where we said it won't work, this one, current was coming from the pole into the throws, and the voltage polarity was the same. I want to create the same voltage polarity. So, same voltage polarity, right? Same voltage polarity, but current was going from my load from my pole into the throws. In this case, you would have to choose this circuit, right? And it will be fine. It will work fine. I mean, current can flow in this fashion. Current can flow in this fashion, right? Current can flow in this fashion. This potential is the most negative potential in the circuit, right? That means this potential is a bit higher. That means I can turn on and turn off my switching device as well, right? So I've satisfied the turn on, turn off conditions as well as my current flow conditions. And then, okay, so this is like the current polarity sort of axis, and then this is the voltage polarity axis. So this is for positive throw voltages. You use these two circuits, this or that. And in this case, current is positive, so out of my throws into the pole. Current is negative from my pole into the throws. So it's like different circuits, right? This box that we're interfacing between. You have a source, and you have a load. I remove the filter for now, forget about the filter. This box here will depend on the polarity of the voltage at the input and the direction of current at the output. So if you're doing this, it's different than, you can do anything. You can do voltages, positive, negative, currents, positive, negative. You can do anything you want, right? And you have to choose something in here that will make it happen, right? There's something in here that will make it happen. You can cheat from this, or you can go through the logic that we went through. Okay, current can flow, current will not flow, MOSFET's positive, MOSFET's negative. You can look at the switching characteristics of the diode and the MOSFET. We'll go through an example of that as well. And so this last example, we'll stop. This is the last slide. So this is one way of doing this. Okay, figuring out what do I need to put in the circuit, right? The other way is a way that the book describes. The book goes through a different way, a different approach. So it's fine as well. Yeah. So you have a circuit, you have an input source, and you have an output load. The output load here is a constant current load, right? And you have two switches. You have two switches here. When this switch is on, when switch S1 is on, switch S2 is off, and vice versa. And these are the current and voltage polarities across the switches. Okay? So when switch S1 is on, what current does it conduct? I1. And when it's off, when switch S1 is off, what is the polarity of voltage across S1? What is voltage across S1 equal to? No, I mean this is, V2 is now on. Exactly, it's equal to Vs because this is a short circuit now. This node is exactly this node, and this node here is exactly this node. So V1 is equal to Vs when the switch is off. So it's blocking positive voltage, right? Blocking positive voltage. And when the switch is on, it's conducting forward current, right? So it's blocking positive voltage and conducting forward current. What is the device that we studied that can do that? Blocking positive voltage and conducting forward current, right? Can a diode do this? Can a diode do this job? The diode switching characteristics look like this. It blocks reverse voltage and conducts forward current, right? So a diode cannot be put in this place, right, in place of the S1, but I can put a MOSFET because of the characteristics of the switching characteristics of the MOSFET that we talked about, right? So I can for S1 here, this is the characteristics that I would like. This is what's happening. I want to conduct positive current and I want to block positive voltage when it's off. And then for S2, you go through the same thing. For S2, what's happening? For S2, this is the voltage and current polarity. S2 will conduct positive current when it's closed. It will conduct positive I2 current. How about when it's open? What's the voltage polarity across it? When this is open, this is shorted. So this node is exactly this node, and this node is exactly this node. So V2 voltage is negative, right? It's negative Vs. Right? So it's negative Vs. So it's blocking negative voltage. Right? So it blocks negative voltage and conducts positive current. What is the device that can do that? The diode can do that. Right? So if the diode can do that, then this is what I need to stick in the circuit in that case. Right? So this is the circuit that we just went through. So I will explain this next time, but you see the logic. So we went through the circuit, looked at the operating conditions, and we selected the devices that can fit. Okay? Or you can use my nice cheat sheet, right? And you can, okay, what do I have on my left-hand side? Vs is positive to the negative. Positive here, negative here, and current is coming out. So what do? So V is positive, so it's either this or that, and current is coming out of my switches. Then it's this circuit. If current was coming into, I would use, So this is like a nice cheat sheet, if you want to. And then we will do a trick later where we can actually combine those. Combine spheres and stuff. So this wraps up chapter 1. The rest was just, I was just giving you some idea of ratings of commercial devices. I think we went to that in the first class as well. Just to tell you that the SCRs are the workhorse of the high power. IGBTs are, a lot less voltage, a lot less current, but they are used. And then Mu'in will go through the simulation work in the lab, So the rest of the slides are just some simulation work that you will go through in the lab. Yeah. So we're done with chapter 1. I will post the homework to the website today, and you will